So here's something that might surprise you. The most accurate theory in the history of science, the one that has been tested and confirmed to more decimal places than any other prediction humans have ever made, is also one of the most confusing. And I don't mean confusing in the way that, say, general relativity is confusing, where you can at least picture curved spacetime if you squint hard enough. I mean confusing in a way that has made some of the smartest people who ever lived throw up their hands and say, essentially, I don't fully understand this either, but it works. It works absurdly well. That theory is quantum field theory, and tonight we're going to walk through it. Slowly, gently. Not because we need to rush anywhere. There's no exam at the end of this. But because it's one of those subjects where the slower you go, the more beautiful it gets. And if you drift off somewhere along the way, that's perfectly fine. That's kind of the point. You're here to relax, and I'm here to talk about one of the strangest, most wonderful frameworks that human beings have ever constructed. So settle in. Let's start at the very beginning, because the beginning is actually a really good story. The year is 1900. The place is Berlin. And a physicist named Max Planck is having a terrible time. Now, Planck wasn't some young radical trying to overthrow physics. He was the opposite. He was conservative, methodical, deeply respectful of the classical physics that had been built up over centuries. He loved thermodynamics. He was the kind of person who wanted everything neat and orderly, who believed that the existing laws of physics were fundamentally correct and just needed a little tidying up in a few spots. And one of those spots, one of those little problems that seemed like it should have a straightforward answer, involved something called blackbody radiation. Here's the idea. Imagine you have an object, any object, and you heat it up. As it gets hotter, it glows. First a dull red, then orange, then white, then bluish white. You've seen this with a stovetop burner or the filament inside an old incandescent light bulb. The question physicists were asking was simple. Can we predict exactly how much light an object emits at each color, at each wavelength, for a given temperature? It seemed like a perfectly reasonable thing to calculate using the physics they already had. Maxwell's beautiful equations of electromagnetism and the well-established laws of thermodynamics. But when they tried, something went horribly wrong. The formulas they derived worked fine for long wavelengths, for infrared light and red light. But as you moved toward shorter wavelengths, toward ultraviolet light, the prediction didn't just get a little bit off. It predicted that the object should be emitting infinite energy in the ultraviolet range. Infinite, which is, a problem. You don't want your equations telling you that a warm oven should be blasting out infinite ultraviolet radiation. This was so clearly absurd that it got a dramatic name, the ultraviolet catastrophe. And this is where Planck comes in. He spent months, really, the better part of 1900, trying to find a mathematical formula that would match the actual experimental data, the real measurements of how hot objects radiate. And he found one. He found a formula that fit the data beautifully. But here's the thing that bothered him, the thing that kept him up at night. To make his formula work, he had to assume something that didn't make any sense within classical physics. He had to assume that energy wasn't continuous. Let me explain what that means, because it's one of those ideas that sounds simple but is actually revolutionary. In classical physics, energy is like water flowing from a faucet. You can have any amount you want. You can turn the faucet just a tiny, tiny bit and get the smallest trickle. Energy is smooth, continuous, infinitely divisible. But Planck's formula only worked if he assumed that energy came in little packets, discrete chunks, like individual drops of water, instead of a smooth stream. He called these chunks quanta, from the Latin word for how much, and the size of each quantum depended on the frequency of the light. Higher frequency light, like ultraviolet, came in bigger packets. Lower frequency light, like infrared, came in smaller ones. The relationship was beautifully simple. The energy of one quantum equals the frequency of the light multiplied by a constant. That constant is now called Planck's constant, and it's one of the most fundamental numbers in all of physics. It's tiny, incredibly tiny, which is why we don't notice this graininess in everyday life. But it's there. Now, here's what's fascinating about Planck himself. He didn't really believe this was how nature actually worked. He thought it was a mathematical trick, a clever accounting device that happened to give the right answer. He figured someone smarter would come along eventually and explain why the trick worked without needing to take it literally. Energy isn't really chunky, he thought. It can't be. That would be insane. But then, 5 years later, in 1905, a young patent clerk in Bern, Switzerland, took Planck's idea and ran with it in a direction that Planck never intended. That patent clerk, of course, was Albert Einstein, and the paper he wrote, not the one about relativity, the other one, the one that would actually win him the Nobel Prize, was about the photoelectric effect. The photoelectric effect was another one of those annoying little puzzles that classical physics couldn't explain. Here's the setup. You shine light on a metal surface, and sometimes electrons pop off. That much made sense. Light carries energy, and if enough energy hits an electron, it should be able to knock it free. But the details were all wrong. Classical physics predicted that if you used brighter light, more intense light, you should be able to knock off electrons no matter what color the light was. Just crank up the brightness. But that's not what happened. What actually happened was that below a certain frequency, below a certain color threshold, no electrons came off at all, no matter how bright you made the light. You could blast that metal surface with the most intense red light imaginable and nothing would happen. But switch to a dim ultraviolet light, barely a whisper of it, and electrons would start popping off immediately. Einstein's explanation was elegant and radical. Light, he said, isn't just a wave. It actually does come in those little packets that Planck described. Each packet, each quantum of light, which we now call a photon, carries a specific amount of energy determined by its frequency. When a photon hits an electron, it's an all-or-nothing interaction. Either that single photon has enough energy to knock the electron free, or it doesn't. 1,000 low-energy photons can't pool their energy together to do the job. It's like trying to break down a door. One person pushing really hard might do it, but 100 people each pressing with one finger won't, even though the total force might be the same. Each interaction is individual, discrete, quantized. Think about what that means for a second. Einstein wasn't just saying that energy is absorbed in chunks, which was already weird enough. He was saying that light itself, the thing that Maxwell had so beautifully described as a smooth, continuous electromagnetic wave, actually has a particle-like nature. It comes in individual pieces. This was, to put it mildly, controversial. Even Planck thought Einstein had gone too far. Light is a wave. Everyone knew that. Thomas Young had proven it with his double-slit experiment more than a century earlier. You could see the interference patterns. Waves interfere. Particles don't. Light is a wave. End of discussion. Except it wasn't the end of the discussion. It was the beginning of a much stranger one. Because here's the problem that was now staring physics in the face. Light seemed to be both a wave and a particle, depending on how you looked at it. In some experiments, it behaved exactly like a wave, spreading out, interfering with itself, diffracting around corners. In other experiments, it behaved exactly like a particle, arriving in discrete lumps, knocking electrons off metals one photon at a time. And this wasn't a matter of our instruments being imprecise. It was fundamental. Light genuinely seemed to have this dual nature, and no one had a good framework for understanding how that could be. This is the period, roughly 1900 to 1925, that physicists sometimes call the old quantum theory. It's a messy, fascinating, frustrating era where brilliant people were stumbling around in the dark, finding pieces of a puzzle, but not yet seeing the whole picture. And the next big piece came from an unexpected direction. In 1913, a young Danish physicist named Niels Bohr proposed a model of the atom that was, frankly, a bit of a Frankenstein creation. It bolted quantum ideas onto a classical framework in a way that shouldn't have worked but did. Here's what he did. The picture of the atom at the time, thanks to Ernest Rutherford's experiments, was a tiny dense nucleus with electrons orbiting around it, like planets around a sun. But this picture had a fatal flaw. According to classical electromagnetism, an electron moving in a circle is accelerating, and an accelerating charged particle must radiate energy. So the electron should be continuously losing energy, spiraling inward, and crashing into the nucleus in a fraction of a second. Every atom in the universe should collapse almost instantly, which, you may have noticed, doesn't happen. Bohr's fix was audacious. He simply declared that electrons could only exist in certain specific orbits, certain allowed energy levels, and that while they were in those orbits, they didn't radiate. They just didn't. He couldn't explain why. He just postulated it. And when an electron jumped from a higher energy orbit to a lower one, it emitted a photon whose energy exactly matched the difference between the two levels. This explained why atoms emit light only at specific wavelengths, those sharp, bright spectral lines that scientists had been cataloging for decades without understanding. Hydrogen, for instance, emits a very specific red line, a specific blue-green line, a specific violet line. Bohr's model predicted these wavelengths with stunning accuracy. But it was clearly an incomplete theory. It worked beautifully for hydrogen, with its single electron, and got increasingly unreliable for heavier atoms. And it had no real justification for its core assumption. Why should only certain orbits be allowed? What made those orbits special? Bohr essentially said, because the math works if I assume this, which is honest but not exactly satisfying. The answer to that question, why certain orbits, why certain energy levels, why this strange discreteness, would come about a decade later, and it would come from a realization that was even stranger than anything that had come before. If light, which everyone thought was a wave, could behave like a particle, then maybe particles, like electrons, which everyone thought were, well, particles, could behave like waves. This idea was proposed in 1924 by a French physicist named Louis de Broglie, and it was his doctoral thesis, which is a pretty bold move when you think about it. He was essentially saying that everything has a wavelength. You, me, a baseball, an electron, everything. The wavelength is related to the object's momentum, and for anything with everyday scale, mass, and speed, the wavelength is so incomprehensibly tiny that it's completely undetectable. But for something as small and light as an electron, the wavelength is on the scale of atomic distances. And suddenly, Bohr's mysterious allowed orbits made sense. They were the orbits where the electron's wave fit perfectly around the nucleus, a whole number of wavelengths around the circumference, like a standing wave on a vibrating guitar string. The orbits where the wave didn't fit, where it would destructively interfere with itself, simply couldn't exist. De Broglie's thesis committee, by the way, wasn't sure what to make of it. They sent it to Einstein for a second opinion, and Einstein reportedly said it was very interesting, which in Einstein's vocabulary was high praise. Within a few years, the wave nature of electrons was confirmed experimentally by Clinton Davison and Lester Germer at Bell Labs, and independently by George Paget Thomson in Scotland, who, in one of history's lovely ironies, was the son of J.J. Thomson, the man who had discovered the electron as a particle in the first place. The father won a Nobel Prize for showing that the electron is a particle. The son won a Nobel Prize for showing that the electron is a wave. Both were right, so by the mid-1920s, the situation in physics was exhilarating and deeply unsettling. Everything, light, electrons, all of it, seemed to have this dual wave-particle nature. The old classical picture, where waves are waves, and particles are particles, and never the twain shall meet, was broken beyond repair. What was needed was a completely new mathematical framework, a new language that could naturally accommodate this duality, that could predict the outcomes of experiments with precision. And in 1925 and 1926, that framework arrived, almost simultaneously, from two very different directions, built by two very different people who didn't particularly like each other. One was a young, intense German physicist named Werner Heisenberg. The other was an older, more elegant Austrian named Erwin Schrödinger. And the theories they built looked nothing alike on the surface, which made what happened next all the more remarkable. Because it turned out they were secretly the same theory, wearing completely different disguises. Let's start with Heisenberg, because he got there first, if only by a few months, and because his story has this wonderful quality of a young man throwing out everything he'd been taught and starting from scratch. Werner Heisenberg was 23 years old in the summer of 1925. 23. He'd been working with some of the greatest minds in physics, Max Born in Göttingen, Niels Bohr in Copenhagen, and he was frustrated. All these models of the atom, Bohr's orbits, de Broglie's waves, they kept talking about things you couldn't actually see. Nobody had ever watched an electron orbit a nucleus. Nobody had ever directly measured the trajectory of an electron inside an atom. And Heisenberg had this radical, almost philosophical conviction that physics should only deal with things you can actually observe. Measurable quantities. Things that show up in experiments. So what can you actually observe about an atom? You can observe the light it emits. You can measure the frequencies of spectral lines, and you can measure how bright those lines are. That's it. That's what nature gives you. And Heisenberg decided to build an entirely new mechanics, a new way of calculating how quantum systems behave, using only those observable quantities. No orbits, no trajectories, no pictures of little balls going around in circles. Just the numbers that come out of experiments, organized into mathematical tables. Now, the story goes that Heisenberg had terrible hay fever that spring, and he retreated to Helgoland, this tiny windswept island in the North Sea off the German coast, to recover. And there, alone on this rocky island, barely able to breathe through his swollen sinuses, he worked through the night on his new theory. He later described a moment in the early hours of the morning when the pieces clicked into place, and he was so excited he went out and climbed a rock on the island and watched the sun rise. He felt he was looking through the surface of atomic phenomena down to a strangely beautiful interior, as he put it, which is a remarkably poetic thing for a guy surrounded by used handkerchiefs on a barren island. What he'd constructed was something that would come to be called matrix mechanics. The key mathematical objects weren't simple numbers. They were arrays of numbers, grids, what mathematicians call matrices. And here's the strange thing that fell out of his calculations almost immediately, something that startled even Heisenberg. When you multiplied two of these matrices together, the order mattered. If you had two quantities, let's call them A and B, then A times B was not the same as B times A. In ordinary arithmetic, of course, 3 times 5 is the same as 5 times 3, 15 either way. But in Heisenberg's quantum mechanics, that rule broke down. The order of operations mattered. This might sound like a mathematical curiosity, but think about what it means physically. Those matrices represented measurable things, position and momentum, for instance. And the fact that position times momentum didn't equal momentum times position meant something profound. It meant you couldn't simultaneously know both of them with perfect precision. The universe itself had a built-in fuzziness, a fundamental limit on what could be known. This would eventually crystallize into Heisenberg's uncertainty principle, which he published in 1927, but the seeds of it were right there in those matrices on Helgoland. The math was telling him something about reality that nobody had anticipated. Now, Heisenberg brought his work back to Göttingen, to Max Born, and Born recognized those mathematical objects. He said, essentially, "Werner, these are matrices. Mathematicians have been studying these for decades." Born, along with his student Pascual Jordan, helped Heisenberg formalize the theory into a rigorous mathematical framework. The three of them published what's sometimes called the Drei-Männer-Arbeit, the three-man paper, in late 1925, and it was a complete quantum mechanics. It could predict the energy levels of atoms, the intensities of spectral lines, all of it. It worked. But here's the thing, almost nobody liked it. Physicists are human beings, and human beings like to visualize things. They like pictures. They like to imagine an electron doing something, going somewhere, following some kind of path. And matrix mechanics gave you none of that. It was abstract, it was algebraically dense, and it felt, to many physicists, like doing accounting rather than doing physics. You cranked through these arrays of numbers and out popped the right answers, but you had no intuitive sense of what was happening. It was like being handed a correct answer to a question you didn't understand. Enter Erwin Schrödinger. And what a contrast he was. Where Heisenberg was young, intense, and somewhat ascetic in his approach, Schrödinger was in his late 30s, worldly, a man of broad cultural interests, and, let's say, an unconventional personal life. He was Austrian, charming, and he loved the classical tradition in physics. He loved waves. He loved continuous, smooth, visualizable mathematics. And when he encountered de Broglie's idea that particles have wave properties, something clicked for him. Schrödinger went on a holiday to the Swiss Alps in late December 1925 to a villa in Arosa. He brought with him de Broglie's thesis, some physics notes, and, according to various historical accounts, a companion who was not his wife. The precise identity of this mystery woman has been debated by historians for decades, and we'll probably never know for sure. But whoever she was, Schrödinger returned from that holiday with one of the most important equations in the history of science. Over the first few months of 1926, he published a series of papers that laid out what we now call wave mechanics, built around the Schrödinger equation. And the Schrödinger equation was beautiful. It described the electron not as a particle with a definite position and velocity, but as a wave, a smooth, continuous wave function that spread out through space. You could write it down, you could visualize it, you could see the waves sloshing around inside the potential well of an atom, forming standing wave patterns that corresponded to different energy levels. It felt like physics. It felt like something you could wrap your mind around. And it gave exactly the same answers as Heisenberg's matrix mechanics for every problem anyone tried. Physicists loved it. They could picture what was going on. They could use the familiar tools of calculus, differential equations, the kind of math they'd grown up with. Schrödinger's equation swept through the physics community like a relief. It was like someone had translated a book from an alien language into your mother tongue. And Heisenberg was furious. He wrote to Wolfgang Pauli, another brilliant young physicist and one of the great sharp tongues in the history of science, saying something to the effect that the more he thought about Schrödinger's theory, the more disgusting he found it. He felt that Schrödinger was papering over the truly revolutionary aspects of quantum mechanics, making it look classical and comfortable when the whole point was that nature wasn't classical or comfortable. Schrödinger, for his part, said that he was repelled by Heisenberg's approach, that he found it, and this is close to a direct quote, repulsive, and that he was discouraged, if not repelled, by what he considered its lack of visualizability. So you had these two camps, the matrix mechanics people, centered in Göttingen and Copenhagen, and the wave mechanics people, with Schrödinger in Zurich and many of the older generation of physicists rallying around him. It was a genuine intellectual rivalry, and it got personal. But here's the kicker. It didn't last long, because Schrödinger himself proved that the two theories were mathematically equivalent. In one of his 1926 papers, he showed that you could derive matrix mechanics from wave mechanics and vice versa. They were the same theory expressed in different mathematical languages. Every prediction one made, the other made identically. It was like discovering that two people who seemed to be arguing in completely different languages were actually saying exactly the same thing. This was a deep result, and it's worth sitting with for a moment. Two physicists, starting from completely different philosophical commitments, one saying, only deal with observables, throw away all pictures, the other saying, everything is waves, smooth and continuous, arrived at the same mathematical structure. That tells you something important about the theory. It's not just a human invention, a convenient fiction. There's something real underneath it, something that doesn't care how you choose to describe it. The physics is the physics, regardless of the language you write it in. Now, the mathematical framework that unified both approaches would eventually be polished and generalized by Paul Dirac in Cambridge and John von Neumann in Göttingen, and it became what we now call quantum mechanics in its modern form. The state of a quantum system lives in an abstract mathematical space called a Hilbert space. Observable quantities correspond to mathematical operators that act on that space. And the wave function, Schrödinger's beloved wave function, is just one particular way of representing the state, one particular choice of basis, as a mathematician would say. Heisenberg's matrices are another. Same room, different windows. But there was still a massive problem lurking underneath all of this, and it's the problem that would eventually drive physicists toward quantum field theory. The Schrödinger equation, as beautiful as it was, had a limitation that Schrödinger himself recognized almost immediately. It wasn't compatible with Einstein's special relativity. It treated time and space differently. Space appeared as a variable in the wave function, but time was just a parameter, ticking along in the background. In special relativity, time and space are supposed to be intertwined, woven together into a unified space-time. The Schrödinger equation was fundamentally non-relativistic. It worked beautifully for slow-moving electrons and atoms, but it couldn't handle particles moving close to the speed of light, and it couldn't naturally describe the creation and destruction of particles, which is something that relativity implies should be possible when enough energy is involved. And this is where a young Paul Dirac enters the story. And honestly, Dirac might be the most fascinating character in all of 20th century physics. He was born in Bristol, England, in 1902, the son of a Swiss-French father who taught French at a local school, and who, by many accounts, was a cold and domineering man. Dirac grew up quiet, almost pathologically reserved. He spoke only when he had something precise to say. His colleagues would later joke about the Dirac as a unit of measurement, 1 word per hour. He was awkward in social situations, seemingly indifferent to small talk, and yet his mind was extraordinary. He thought in mathematics the way a poet thinks in metaphor, fluently, instinctively, and with an aesthetic sense that guided him toward equations that were not just correct, but beautiful. In 1928, Dirac set out to write a version of quantum mechanics that was consistent with special relativity. He wanted an equation for the electron that treated space and time on equal footing, the way Einstein's theory demanded. And what he found was something that stunned him, something that stunned everyone. Because the equation he wrote down didn't just describe the electron, it described a universe far stranger than anyone had imagined. Let's slow down here, because the Dirac equation is one of those moments in physics where you can almost feel the ground shifting under your feet. Dirac's goal was straightforward enough in principle: take quantum mechanics, take special relativity, and make them work together for the electron. Others had tried. There was already an equation called the Klein-Gordon equation, proposed independently by Oscar Klein and Walter Gordon in 1926, which was relativistic and quantum mechanical. But it had problems. It produced negative probability densities, which, if you think about it, is a bit like saying there's a minus 30% chance of finding a particle somewhere. That's not physically meaningful. It's nonsense. Dirac wasn't satisfied with it, and he suspected the issue was that the Klein-Gordon equation was second order in time, meaning it involved the second derivative of the wave function with respect to time. The Schrödinger equation, by contrast, was first order in time. Dirac wanted something that was first order in time, like Schrödinger's, but also first order in space, which relativity demanded for consistency, since space and time should be treated symmetrically. And here's where his mathematical instinct, that almost aesthetic sense of rightness, really came through. He sat down and asked himself a deceptively simple question. Can I take the square root of the Klein-Gordon equation? Now that sounds almost absurd. You don't normally take the square root of an equation in physics and expect something meaningful to fall out. But Dirac realized that if he allowed the coefficients in his equation to be not ordinary numbers but matrices, specifically 4x4 matrices, then he could write a first-order equation that, when squared, gave back the Klein-Gordon equation. It was a mathematical trick of breathtaking elegance. He needed 4-component objects instead of simple 1-component wave functions, and he needed these special matrices, now called gamma matrices, that satisfied very particular algebraic relationships. And when he put it all together, in January 1928, he had his equation, the Dirac equation. And it was beautiful. But here's the thing, and this is what makes physics so endlessly surprising. The equation immediately told him things he hadn't asked for, things he hadn't expected, things nobody had expected. The first gift was spin. Before Dirac, physicists knew that electrons behaved as if they were spinning. They had an intrinsic angular momentum that gave them a tiny magnetic moment. This had been proposed by Goudsmit and Uhlenbeck in 1925, essentially as an add-on, a postulate tacked onto quantum mechanics because experiments demanded it. Nobody really understood where spin came from. It was just there. But in Dirac's equation, spin appeared automatically. It wasn't put in by hand. It fell out of the mathematics as a natural consequence of combining quantum mechanics with special relativity. The electron had to have spin 1/2. The equation demanded it. Think about what that means. By insisting that quantum mechanics and relativity play nicely together, Dirac discovered that a fundamental property of matter, one that had seemed arbitrary and mysterious, was actually inevitable. It had to be that way. That's the kind of thing that gives physicists chills. The second gift was even more dramatic and far more troubling. When Dirac solved his equation, he found that it had solutions with positive energy, which was fine. Those described ordinary electrons doing ordinary things. But it also had solutions with negative energy. And not just a few. For every positive energy solution, there was a corresponding negative energy solution. Now, in classical physics, you might just ignore negative energy solutions as unphysical, wave them away, say they're mathematical artifacts. But in quantum mechanics, you can't do that so easily. Quantum mechanics allows transitions. An electron in a positive energy state should be able to emit a photon and drop into a negative energy state, releasing energy as it falls. And then it should keep falling, lower and lower, emitting infinite amounts of energy. Every atom in the universe should be catastrophically unstable. The whole thing should have collapsed in an instant. This was not a small problem. This was an existential crisis for the theory. Dirac thought about this for a while, and in 1930, he proposed something audacious. What if, he said, all the negative energy states are already filled? What if the vacuum, empty space itself, is actually a sea of electrons occupying every possible negative energy state? If that were the case, then the Pauli exclusion principle, which says no two electrons can occupy the same quantum state, would prevent any positive energy electron from dropping down. The negative energy states would be full. The vacuum would be stable. This idea became known as the Dirac sea, and it's one of the wildest concepts in the history of physics. Empty space isn't empty at all. It's an infinite ocean of negative energy electrons, and what we call the vacuum is just the state where every negative energy seat is taken. But then Dirac took it one step further, and this is where it gets really interesting. If the vacuum is a filled sea of negative energy, electrons, what happens if you knock one of those electrons out? Say a high-energy photon comes along and kicks a negative energy electron up into a positive energy state. You'd see the newly promoted electron. That's just a regular electron appearing. But you'd also see a hole in the sea, a missing negative energy electron. And here's the kicker. A hole in a sea of negative energy. Negatively charged electrons would look, to any observer, like a particle with positive energy and positive charge. It would look like an electron, but with the opposite charge. Dirac initially hesitated to say this outright. In his 1930 paper, he speculated that the hole might be the proton, since the proton was the only known positively charged particle at the time. But that didn't work. The proton is nearly 2,000 times heavier than the electron, and the symmetry of the equation demanded that the hole have exactly the same mass as the electron. Robert Oppenheimer and Hermann Weyl, among others, pointed this out. And so, by 1931, Dirac made the bold prediction: there must exist a particle identical to the electron, but with positive charge, an anti-electron. He called it, in his understated way, a new kind of particle unknown to experimental physics. And then, in 1932, a young American physicist named Carl Anderson, working at Caltech, found it. Anderson was studying cosmic rays, high-energy particles raining down from space, using a cloud chamber, which is a device filled with supersaturated vapor, where charged particles leave visible trails as they pass through. Anderson had placed his cloud chamber in a strong magnetic field, which causes charged particles to curve. Positive charges one way, negative charges the other. And in his photographs, he kept seeing tracks that curved the wrong way. They curved like an electron would, with the same gentle radius, but in the opposite direction. They couldn't be protons. Protons are heavy and leave thick, stubborn tracks. These tracks were light and delicate, just like electron tracks, but bending as if the particle carried a positive charge. Anderson called it the positron, and its discovery confirmed Dirac's prediction in spectacular fashion. It also confirmed something much deeper. Antimatter was real. For every particle, there existed an antiparticle with the same mass but opposite charge. This wasn't just a quirk of electrons. It was a universal principle. And it came straight out of the mathematics of the Dirac equation. Dirac hadn't gone looking for antimatter. He'd been trying to write a consistent equation for the electron, and the universe handed him a mirror image he never asked for. Now, let's pause here for a moment, because I want you to appreciate the sheer strangeness of what just happened in the story of physics. A theorist, sitting in his room in Cambridge, manipulating symbols on paper, trying to make two theories consistent with each other, predicts the existence of an entirely new form of matter that no one had ever seen or even suspected. And then, an experimentalist on the other side of the world finds it, exactly as predicted. This is the unreasonable effectiveness of mathematics that Eugene Wigner would later write about. The equations know things we don't. But the Dirac equation, for all its triumphs, also revealed the limits of what a single particle equation could do. The Dirac sea was clever, but it was also deeply uncomfortable. You had to accept that the vacuum contained an infinite number of particles. You had to subtract infinities to get finite answers. And the whole picture of knocking electrons out of a sea to create positrons was really a story about particle creation and destruction. A photon comes in, an electron-positron pair comes out. You couldn't describe that naturally within the framework of ordinary quantum mechanics, where the number of particles is fixed. The Schrödinger equation describes one particle, or two, or 10, but always a definite number. The Dirac equation was screaming at physicists that the number of particles is not fixed. Particles can be born. Particles can die. The vacuum itself is seething with potential. And this is the crucial realization that pushes us beyond quantum mechanics into quantum field theory. You need a framework where the fundamental objects aren't particles at all. They're fields, and particles are just excitations of those fields, the way waves are excitations of the ocean surface. An electron isn't a little ball that exists independently. It's a ripple in the electron field, a quantum of excitation in a field that permeates all of space-time. A photon isn't a little bullet of light. It's a quantum of the electromagnetic field. And when a photon creates an electron-positron pair, what's really happening is that energy is being transferred from one field to another. The electromagnetic field loses a quantum, and the electron field gains two quanta, one electron and one positron. This idea, that fields are fundamental and particles are derived, is the conceptual heart of quantum field theory. And it didn't arrive all at once. It was built up piece by piece through the late 1920s and into the 1930s by several physicists working in parallel, often struggling with mathematical difficulties that seemed insurmountable. The person who took the first real step was once again Dirac. In 1927, even before his famous equation, Dirac published a paper on the quantum theory of the emission and absorption of radiation. In this paper, he took the classical electromagnetic field and applied quantum mechanics to it. He quantized the field itself. He treated the electromagnetic field as a collection of harmonic oscillators, one for each possible mode of vibration, and then applied the rules of quantum mechanics to those oscillators. Each oscillator could be in its ground state, or its first excited state, or its second, and so on. And the number of quanta in each oscillator corresponded to the number of photons with that particular frequency and direction. When an atom emitted a photon, the oscillator gained one quantum. When an atom absorbed a photon, the oscillator lost one quantum. This was the birth of quantum electrodynamics, QED, the quantum field theory of light and charged particles. But Dirac's 1927 paper, groundbreaking as it was, only quantized the electromagnetic field. The electron was still treated as a regular quantum mechanical particle, described by a wave function. It wasn't until the work of Pascual Jordan, along with contributions from Heisenberg, Pauli, and others in the late 1920s and early 1930s, that physicists began to quantize the electron field as well. Jordan, in particular, had a deep insight. You could take the Dirac equation, reinterpret the wave function not as a probability amplitude for a single particle, but as a field operator, a quantum field. And then the excitations of that field would automatically describe electrons and positrons, with particle creation and annihilation built right in. This procedure, sometimes called second quantization, was the key conceptual leap. First quantization gives you quantum mechanics, particles behaving as waves. Second quantization gives you quantum field theory, fields behaving as particles. And this is where the story starts to get both incredibly powerful and incredibly messy. Because as soon as physicists tried to calculate anything beyond the simplest processes in this new quantum field theory, they ran into problems that seemed to break the entire theory. Infinities. Not just big numbers, actual, honest-to-goodness infinities that showed up in the middle of calculations and refused to go away. And for nearly 2 decades, from the early 1930s through the mid-1940s, these infinities nearly killed quantum field theory. Some of the smartest people alive seriously considered throwing the whole framework out and starting from scratch. That's the story we need to talk about now, because it's one of the most dramatic intellectual struggles in the history of physics, and the resolution, when it finally came, was so strange, so philosophically uncomfortable, and so spectacularly successful that we're still arguing about what it really means. So, let's set the scene. It's the early 1930s. You've got this beautiful new formalism, quantum electrodynamics, where the electromagnetic field is quantized, the electron field is quantized, and in principle, you can calculate anything about how light and matter interact. You want to know the probability that an electron scatters off another electron? QED can tell you. You want to know the rate at which an excited atom emits a photon? QED can tell you. At the lowest level of approximation, the theory works beautifully. You draw a simple picture, Later, these would be called Feynman diagrams, but we'll get to that, where an electron emits a virtual photon. The photon travels to another electron and gets absorbed. You calculate the strength of that interaction, and the answer matches experiment. Wonderful. But here's the thing. That lowest level calculation is just the first term in what's supposed to be an infinite series. It's like the first term in a Taylor expansion, if that analogy helps. You're supposed to add corrections, higher order terms, where more complicated things happen. Maybe the photon, while it's traveling between the two electrons, briefly splits into a virtual electron-positron pair, which then annihilates back into a photon. Or maybe the electron, before it emits the photon, emits and reabsorbs a virtual photon of its own, a little loop of self-interaction. These processes are supposed to be small corrections. They're suppressed by powers of the fine structure constant, alpha, which is roughly 1 over 137, a small number. So you'd expect the corrections to be about 1% of the leading term. Manageable. Important for precision, but not dominant, except when you actually sit down and calculate these corrections, you get infinity. Not a big number. Infinity. The integral diverges. It blows up. Let me try to give you a feel for why. Take the simplest example, the self-energy of the electron. An electron, just sitting there in empty space, can emit a virtual photon and then reabsorb it. This is allowed by quantum mechanics. The uncertainty principle lets you borrow energy for a short time, as long as you pay it back quickly. Now, that virtual photon can have any energy and any momentum, up to arbitrarily high values. When you calculate the total contribution of all these virtual photons to the electron's energy, you have to integrate over all possible momenta, and the integral doesn't converge. The contributions from very high momentum virtual photons, what physicists call the ultraviolet region, by analogy with high-frequency light, just keep growing without bound. The electron's self-energy comes out infinite. And this isn't some exotic, obscure problem. This is the mass of the electron. The theory is telling you that the electron has infinite mass, which is, to put it mildly, not what we observe. The same kind of infinity shows up in another fundamental quantity, the charge of the electron. When you calculate how the electron's charge gets modified by virtual processes, by the cloud of virtual electron-positron pairs that constantly pop in and out of existence around it, screening the bare charge, you again get a divergent integral. The effective charge comes out infinite or zero, depending on how you look at it. Either way, it's nonsensical. Now here's what's important to understand. This wasn't a surprise that came out of nowhere. People had actually been worrying about the self-energy problem since the days of classical electrodynamics, long before quantum mechanics. If you model the electron as a tiny charged sphere, its own electric field carries energy, and that energy contributes to the electron's mass. As you shrink the sphere toward a point, the self-energy diverges. It goes to infinity. Classical physics already had this problem. What quantum field theory did was make it worse, because now you had not just the classical self-energy, but also quantum corrections on top of it, and those diverged too, even more severely. By the mid-1930s, the situation was genuinely dire. Oppenheimer, yes, the same Oppenheimer who would later lead the Manhattan Project, was one of the first to clearly identify the divergence problem in QED, publishing a paper in 1930, showing that the electron's self-energy was logarithmically divergent in quantum electrodynamics. Weisskopf, a brilliant Austrian physicist who had studied under both Bohr and Pauli, refined the calculation and showed that while quantum effects actually made the divergence milder than the classical case, logarithmic rather than linear, it was still infinite. That was some comfort, but not much. An infinity is an infinity, no matter how slowly it grows. Dirac himself was deeply troubled. He tried various approaches to tame the infinities, none of which really worked. Heisenberg struggled with it. Pauli, who was famous for his sharp tongue and his intolerance for sloppy thinking, was characteristically blunt about the whole mess. The general mood among leading theorists was that something was fundamentally wrong, that quantum field theory, despite its beautiful structure, was somehow broken at its core, and that a completely new framework would be needed. And then the war intervened. From roughly 1939 to 1945, most of the physicists who might have been working on quantum field theory were instead working on radar, nuclear weapons, or other military projects. The Manhattan Project alone absorbed an enormous fraction of the world's theoretical physics talent. In a strange way, though, the war years weren't entirely lost time for QED. The intensive work on radar, in particular, pushed the development of microwave technology to extraordinary precision, and that precision would turn out to be exactly what was needed to force the issue when physicists returned to fundamental physics after the war. Here's what I mean. In 1947, Willis Lamb, working at Columbia University, performed one of the most consequential experiments in the history of physics. Using microwave techniques that had been developed for radar during the war, Lamb measured the energy levels of hydrogen with unprecedented precision, and he found something that shouldn't have been there according to Dirac's equation. The Dirac equation predicted that two particular energy levels of hydrogen, the two S1/2 and two P1/2 states, if you want the technical labels, should have exactly the same energy. They should be degenerate. But Lamb showed they weren't. There was a tiny splitting between them, about 1,000 megahertz, a tiny but unmistakable shift. This became known as the Lamb shift, and it was a direct, measurable consequence of exactly those quantum field theoretic corrections, the virtual processes, the self-energy effects that had been producing infinities in the calculations. So now the situation was exquisite and agonizing at the same time. Experiment was clearly telling physicists that these quantum corrections were real. They had measurable effects, the virtual photons, the virtual electron-positron pairs. They weren't just mathematical artifacts. They shifted energy levels by amounts you could measure in the lab. But the theory, when you tried to calculate those shifts, gave you infinity. The right physics was clearly in there somewhere, buried under the infinities, but no one knew how to extract it. The breakthrough came in a burst of activity between 1947 and 1949, and it involved three very different physicists working in three very different styles, arriving at essentially the same solution by completely different routes. Their names were Shinichiro Tominaga, Julian Schwinger, and Richard Feynman, and the story of how they cracked the problem is one of the great tales of 20th century science. Tominaga was first, chronologically, though the world didn't know it right away. Working in wartime Japan, largely isolated from the Western physics community, Tominaga had developed a fully relativistic formulation of quantum electrodynamics and had begun to show how the infinities could be systematically handled. His key insight, building on earlier work by Dirac, was to formulate the theory in a way that treated space and time on equal footing at every step, a manifestly covariant approach. He and his students showed that the infinities in QED could be absorbed into redefinitions of the electron's mass and charge. The idea was subtle and initially hard to accept. You admit that the bare mass and charge of the electron, the values that appear in the original equations, are themselves infinite, and that the infinite quantum corrections combine with these infinite bare values to produce the finite, measured values we actually observe. You never try to calculate the bare mass or bare charge separately. You only ever calculate differences, and the infinities cancel. This procedure is called renormalization, and if it sounds like a trick, like sweeping infinities under the rug, well, you're not alone in thinking that. Many physicists felt exactly that way. Dirac himself never accepted it. He called it ugly and spent the rest of his career trying to find an alternative. But here's the thing that makes renormalization more than just a trick. It works. Not just qualitatively, not just approximately. It works to extraordinary, almost absurd precision. Schrödinger, at Harvard, arrived at the same conclusion through a very different path. Where Tominaga was quiet and methodical, Schrödinger was a prodigy. He had entered college at 14, got his PhD at 21, and by his late 20s was already considered one of the most formidable calculators in theoretical physics. His approach to QED was mathematically dense, highly formal, and extremely powerful. He developed a complete renormalization framework and used it to calculate the anomalous magnetic moment of the electron, a tiny deviation from the value predicted by the Dirac equation. His result, published in 1948, was alpha over 2 pi, where alpha is the fine structure constant. That's a correction of about 0.00116. And when experimentalists measured it, they got exactly that. Think about what that means for a second. A theory that had been producing infinities that people were ready to abandon was now giving predictions accurate to parts per thousand. And eventually, as the calculations were pushed to higher orders over the following decades, accurate to parts per trillion. The anomalous magnetic moment of the electron remains, to this day, the most precisely confirmed prediction in all of science. Nothing else even comes close. And then there was Feynman, who came at the whole thing from a direction so unorthodox that at first almost nobody understood what he was doing. Feynman had a deep distrust of the existing formalism. He didn't like the way quantum field theory was set up, with its operator-valued fields and its canonical quantization and its dense layer of mathematical machinery. He wanted something more intuitive, more physical. And what he came up with was the path integral formulation, the idea that a quantum particle doesn't take a single path from point A to point B, but rather takes all possible paths simultaneously, and you calculate the probability by summing over all of them, each weighted by a phase factor, determined by the action along that path. From this picture, Feynman developed his famous diagrams, those little pictures with lines and vertices that have become the universal language of particle physics. Each diagram represents a specific mathematical expression, a specific term in the perturbation series. An electron is a straight line. A photon is a wavy line. A vertex where an electron emits or absorbs a photon represents the fundamental interaction. And the beauty of it is that you can read off the rules for calculating any process just by drawing all the possible diagrams and translating them into integrals. The diagrams made quantum field theory calculations almost mechanical, still hard, still requiring skill, but vastly more manageable than the dense operator algebra that Schrödinger and Tominaga used. Feynman's approach also made renormalization feel more physical, or at least more visual. You could see which diagrams produce the infinities. They were the ones with closed loops, where virtual particles circulated with arbitrarily high momenta. And you could see how the renormalization procedure worked. You identified the divergent diagrams, absorbed their infinite contributions into the redefined mass and charge, and everything else came out finite. The three approaches, Tominaga's, Schwinger's, and Feynman's, were eventually shown to be mathematically equivalent by Freeman Dyson, a young British mathematician who had come to the United States and had the rare ability to understand all three frameworks deeply enough to prove their equivalence. Dyson's 1949 papers were a landmark because they not only unified the three approaches, but also provided a systematic proof that QED was renormalizable, that the procedure of absorbing infinities into mass and charge worked not just at the first level of correction, but at every level, to all orders in perturbation theory. You would always get a finite number of types of infinities, and they could always be absorbed into the same physical parameters. All four, Tominaga, Schwinger, Feynman, and Dyson, deserved the Nobel Prize, but the Nobel can only be shared among three. Tominaga, Schwinger, and Feynman received it in 1965. Dyson, despite his crucial contribution, did not, which remains one of the more widely noted omissions in Nobel history. Dyson himself was characteristically gracious about it, but the physics community knew what he had done. So by the early 1950s, QED was on solid ground. The infinities hadn't gone away. They were still there in the formalism. But renormalization provided a rigorous, systematic way to extract finite, meaningful, spectacularly accurate predictions from a theory that naively produced nonsense. And the success of QED raised an obvious, irresistible question. Could the same approach work for the other forces of nature? Because electromagnetism wasn't the only game in town. There was also the strong force, the force that held atomic nuclei together, that bound protons and neutrons into the dense, tiny cores of atoms, and the weak force, responsible for certain kinds of radioactive decay. Could you build quantum field theories for those forces too? Could you quantize them, renormalize them, and extract predictions the way you could with QED? The answer, it turned out, was yes. But the road to get there was far longer and stranger than anyone expected, and it required ideas that would have seemed completely alien to the physicists of the 1940s. It required a new kind of symmetry, a new kind of field, and a new understanding of what a force even is at the quantum level. So let's talk about that. Let's talk about gauge symmetry. The word gauge is one of those terms in physics that sounds like it should mean something mechanical, like a pressure gauge or a wire gauge. And in a way, its origin is almost that mundane. The term traces back to Hermann Weyl in 1929, who used the German word Eigenvarianz, which literally means something like calibration invariance. But the concept itself is far deeper and more beautiful than the name suggests, and once you see it, it changes how you think about every force in the universe. Here's the basic idea, and I want to build it up slowly because it's one of those things that seems abstract at first, but then clicks in a really satisfying way. Think back to what we know about quantum mechanics. A particle is described by a quantum field, and that field has a value at every point in space and time. Now, that value is a complex number. It has a magnitude and a phase. The magnitude tells you about the probability of finding the particle somewhere. But the phase? The phase is like an angle, a kind of internal clock hand pointing in some direction in an abstract space. And here's the thing. if you rotate that phase by the same amount everywhere in the universe, all at once, nothing changes. No experiment you could ever do would detect the difference. The physics is completely invariant under a global phase rotation. This is called a global symmetry, and it's connected, through a beautiful theorem by M.E. Noether from 1918, to the conservation of electric charge. Every continuous symmetry gives you a conserved quantity. That's Noether's theorem. And the global phase symmetry of the electron field gives you charge conservation. Okay, that's nice. But now ask a deeper question. What if you want the freedom to rotate the phase by a different amount at different points in space? Not the same rotation everywhere, but a rotation that varies from place to place and moment to moment, a local phase rotation. Can the physics still be invariant? And the answer is, not automatically. If you just naively let the phase vary from point to point, the equations of motion break. The derivatives in the equation notice the change, because when you're comparing the field at one point to the field at a neighboring point, and their phases have been rotated by different amounts, the derivative picks up an extra term. The math doesn't work anymore. Unless, and this is the key insight, unless you introduce a new field that compensates for those extra terms. A field that transforms in just the right way to cancel out the effects of the varying phase rotation. And when you do that, when you demand local gauge invariance and introduce the compensating field required to make it work, something remarkable happens. The compensating field you're forced to introduce is the electromagnetic field, the photon. The entire structure of electromagnetism, Maxwell's equations, the Lorentz force, all of it, emerges automatically from the requirement that the phase of the electron field can be rotated independently at every point in space-time. Think about what that means for a second. You start with a simple symmetry requirement, the idea that the physics shouldn't care about local phase choices. And out pops the photon. Out pops light. Out pops the force that holds atoms together, that lets you see, that carries radio waves across the ocean. The force isn't something you put in by hand. It's something the symmetry demands. This is the gauge principle, and it's one of the most powerful ideas in all of physics. The technical symmetry group involved for electromagnetism is called U1, the group of rotations in a single complex plane, the circle group. It's the simplest possible continuous symmetry group. And QED, the quantum field theory of electromagnetism, is a U1 gauge theory. Now, by the early 1950s, physicists understood this about QED, at least in retrospect. Whale had planted the seeds, and the gauge structure of electromagnetism was clear. But the burning question was whether the same principle could be extended. Could you build gauge theories based on larger, more complicated symmetry groups? And could those theories describe the strong and weak forces? The first serious attempt came in 1954 from Chen-Ning Yang and Robert Mills, working at Brookhaven National Laboratory. Yang was already a formidable theoretical physicist. He would later share the 1957 Nobel Prize with Sung-Dao Lee for their work on parity violation, which we'll come back to. Mills was a younger physicist, and the Yang-Mills paper would become his most famous contribution. What they did was take the gauge principle and generalize it from the simple U1 group to a more complex group called SU2. Here's why that matters. U1 is abelian. That's a mathematical term meaning the order in which you do operations doesn't matter. Rotate by angle A, then angle B, or rotate by B, then A, you get the same result. But SU of 2 is non-abelian. The order matters. It's like rotations in three-dimensional space, rotating an object around the x-axis. and then the y-axis gives you a different result than rotating around y first and then x. You can try this with a book right now if you're not already drifting off. Flip it one way, then another, and compare. The order matters, and this non-abelian structure changes everything about the resulting gauge theory. When you demand local invariance under SU2 transformations, you're forced to introduce not one compensating field but three gauge bosons instead of one. And here's what's truly wild. Because the symmetry group is non-abelian, these gauge bosons interact with each other. In QED, photons don't carry electric charge, so they don't directly interact with other photons. They're neutral mediators. But in a Yang-Mills theory, the gauge bosons themselves carry the charge of the force they mediate. They talk to each other. The force carriers are also force sources. It's like having mail carriers who are also constantly sending letters to each other while trying to deliver yours. Yang and Mills wrote down the equations for this non-abelian gauge theory, and the mathematical structure was elegant, even beautiful. But there was a serious problem, and it stopped the theory dead in its tracks for years. The problem was mass. Gauge symmetry in its pure form requires the gauge bosons to be massless. The photon is massless, so that's fine for electromagnetism. But the weak force, the force responsible for beta decay, the force that lets neutrons transform into protons, was known to be extremely short-ranged. It only operates over distances smaller than an atomic nucleus. And in quantum field theory, the range of a force is inversely related to the mass of the particle that carries it. A massless carrier gives you an infinite range force, like electromagnetism and gravity. A massive carrier gives you a short-range force. So the carriers of the weak force had to be massive. Very massive, it turned out. But if you just stuck mass terms into the Yang-Mills equations by hand, you destroyed the gauge symmetry, and the theory became non-renormalizable. The infinities came back, and this time, there was no systematic way to absorb them. So you were stuck. You needed massive gauge bosons for the weak force, but gauge symmetry demanded massless ones. It seemed like an impossible contradiction. The resolution came from one of the most clever and subtle ideas in all of 20th century physics, spontaneous symmetry breaking, and the mechanism that made it work, the one that let you have your symmetry and your mass too, would eventually be called the Higgs mechanism. Though, as with so many things in physics, the credit is shared among several people who arrived at related ideas around the same time. The concept of spontaneous symmetry breaking wasn't new to physics. It shows up in condensed matter systems all the time. Think about a ferromagnet, a piece of iron. The underlying laws governing the iron atoms are perfectly symmetric. They don't prefer any particular direction. But below a certain temperature, all the little atomic magnets spontaneously align in one direction. The ground state of the system, its lowest energy configuration, breaks the symmetry that the laws themselves possess. The laws are symmetric, but the solution isn't. Yoichiro Nambu, a Japanese-American physicist at the University of Chicago, was one of the first to bring this idea into particle physics in the early 1960s. Nambu recognized that spontaneous symmetry breaking could explain certain features of the strong force, and his work was deeply influential. He would eventually receive the Nobel Prize in 2008, decades after his key contributions, which tells you something about how long it sometimes takes for the deepest ideas to be fully recognized. But Nambu's version of symmetry breaking came with a catch, a mathematical consequence that seemed like a fatal flaw. Jeffrey Goldstone showed in 1961 that whenever a continuous global symmetry is spontaneously broken, the theory necessarily contains massless scalar particles, massless bosons with no spin. These became known as Goldstone bosons, or Nambu-Goldstone bosons. and the problem was that nobody had ever observed these particles. If they existed, they should have been easy to detect. Their absence seemed to rule out spontaneous symmetry breaking as a viable mechanism in particle physics. But then came the crucial twist. In 1964, several groups of physicists independently realized that when the broken symmetry is a local gauge symmetry rather than a global one, the Goldstone bosons don't appear as physical particles. Instead, they get eaten by the gauge bosons. The degrees of freedom that would have been the massless Goldstone bosons are absorbed into the gauge bosons, giving them mass. The gauge bosons acquire a longitudinal polarization, a new way of vibrating, that massless particles can't have, and this extra degree of freedom is precisely the would-be Goldstone boson in disguise. The massless bosons disappear from the spectrum. The gauge bosons become massive, and the gauge symmetry, while hidden, is still secretly present in the mathematical structure of the theory, which means renormalizability is preserved. This was published in several papers in 1964. Robert Brute and François Englert in Brussels wrote one. Peter Higgs in Edinburgh wrote another, and his paper was notable for explicitly pointing out that the mechanism predicted a new massive scalar particle, a leftover boson, a remnant of the field responsible for the symmetry breaking. Gerald Guralnick, Carl Hagen, and Tom Kibble at Imperial College London published a third paper with a related approach. All three groups deserve credit, though history and the Nobel Committee eventually attached Higgs's name most prominently to the mechanism and to the predicted particle, the Higgs boson. But having the mechanism was one thing. Building a complete, realistic theory of the weak force using it was another challenge entirely. And the person who put the pieces together, who built the first viable unified theory of the electromagnetic and weak forces using non-abelian gauge symmetry and the Higgs mechanism, was someone whose early career had been marked by quiet persistence and a kind of stubborn faith in mathematical beauty. Sheldon Glashow, an American physicist who'd been a classmate of Steven Weinberg's at the Bronx High School of Science in New York, and yes, that's the same Steven Weinberg we're about to talk about, and the fact that two future Nobel laureates sat in the same high school classes is one of those wonderful coincidences that physics history keeps handing us. Glashow had actually proposed a model back in 1961 that tried to unify electromagnetism and the weak force using an SU 2 times U 1 gauge structure. He identified the right mathematical framework, the right group structure, but he couldn't solve the mass problem. His gauge bosons were massless, and he had no way to make them heavy without destroying the theory's consistency. So his model sat there, incomplete, like a building with beautiful architecture, but no roof. Then Steven Weinberg, in 1967, and Abdus Salam, working independently in 1968, took Glashow's gauge structure and married it to the Higgs mechanism, and everything clicked. Weinberg's paper, published in November 1967, under the modest title A Model of Leptons, just 5 pages long, is one of the most cited papers in the history of physics, and for good reason. What Weinberg did was take the SU 2 times U1 gauge symmetry, apply spontaneous symmetry breaking through a Higgs field, and show that the result was a theory where 3 of the gauge bosons acquired mass. These would become the W+, W-, and Z0 bosons that mediate the weak force, while 1 gauge boson remained massless. And that massless boson? That's the photon. Electromagnetism and the weak force, which look completely different in everyday life, were revealed to be 2 aspects of a single unified electroweak force, separated only because the Higgs field broke the symmetry at low energies. Think about what that means for a second. At very high energies, the kind of energies that existed in the first fraction of a second after the Big Bang, there's no distinction between electromagnetism and the weak force. they're one thing. It's only because the Higgs field has a non-zero value everywhere in the universe, filling all of space like an invisible ocean, that these forces look different to us. The photon zips through this ocean without interacting with it, staying massless, traveling at the speed of light. The W and Z bosons interact with it strongly, acquiring masses around 80 and 91 times the mass of a proton respectively, which makes them heavy and sluggish and short-ranged. That's why the weak force only operates over distances smaller than an atomic nucleus. It's not that the force is intrinsically weak in some fundamental sense. It's that its carrier particles are so massive they can barely travel any distance before decaying. Now, here's something that might surprise you. Weinberg's 1967 paper was almost completely ignored when it was first published. For the first few years, hardly anyone cited it. The physics community wasn't sure the theory was renormalizable, that you could actually calculate things with it without getting infinities everywhere. And without that guarantee, it was just a pretty idea. The key question hanging over the whole construction was whether a spontaneously broken non-abelian gauge theory could be renormalized the way QED had been. And the person who answered that question, definitively, was a young Dutch graduate student named Gerard 't Hooft. 't Hooft was working under Martinus Veltman at the University of Utrecht in the Netherlands. Veltman had been laboring for years on the problem of making sense of massive gauge theories, developing computational tools and techniques that most of the physics community wasn't paying much attention to. He was convinced that gauge theories were the right path, and he'd built up a formidable technical machinery for handling them, including one of the first computer algebra programs used in theoretical physics, a program called Schoonship, which is Dutch for clean ship. Veltman had done enormous amounts of groundwork, but the final breakthrough came when 't Hooft, still in his 20s, proved in 1971 that spontaneously broken Yang-Mills theories are indeed renormalizable. Every infinity could be absorbed, every calculation could be made finite and meaningful, just as Tominaga and Schwinger and Feynman had done for QED 2 decades earlier. The effect on the physics community was electric. Almost overnight, Weinberg's neglected 1967 paper became one of the most important in the field. Citations skyrocketed. Suddenly, everyone wanted to work on gauge theories because now they knew the mathematical framework was sound. You could actually use these theories to make predictions, real numerical predictions that could be tested in particle accelerators, and the predictions were extraordinary. The theory said there had to be a Z boson, a neutral carrier of the weak force, which would produce something called neutral current interactions, where particles could exchange a Z boson without changing their electric charge. Nobody had ever observed neutral currents in weak interactions before. In 1973, the Gargamel bubble chamber experiment at CERN found them. The evidence was subtle, neutrinos bouncing off electrons without turning into anything else. But it was there. The electroweak theory had made a prediction, and nature had confirmed it. And then came the really dramatic confirmation. The theory predicted the masses of the W and Z bosons quite precisely. In 1983, a team at CERN led by Carlo Rubbia, using a proton-antiproton collider that Rubbia had championed with almost reckless ambition, discovered both the W and Z bosons at almost exactly the predicted masses. Rubbia is a fascinating character, intense, driven, the kind of person who would bulldoze through bureaucratic obstacles and technical impossibilities with sheer force of will. He and Simon van der Meer, the Dutch engineer who invented the stochastic cooling technique that made the collider work, shared the Nobel Prize in 1984, just a year after the discovery. Glashow, Weinberg, and Salam had already received theirs in 1979, and 't Hooft and Veltman would get theirs in 1999. That's a lot of Nobel Prizes orbiting one theory, and it gives you a sense of how profound the electroweak unification really was. But the electroweak theory was only half the story of what we now call the Standard Model. The other half involved the strong force, the force that holds quarks together inside protons and neutrons, the force that ultimately holds every atomic nucleus together. And the theory of the strong force has its own beautiful and surprising history. Let's go back a bit. By the early 1960s, particle physics was in a state of bewildered abundance. Accelerator experiments kept discovering new particles, dozens and dozens of them, a whole zoo of hadrons, which is the collective name for particles that feel the strong force. There were pions, kaons, etas, rhos, omegas, sigmas, deltas. The list went on and on. It was embarrassing, actually. Physics is supposed to be about simplicity and underlying order, and here was this proliferating menagerie of particles with no obvious organizing principle. Willis Lamb reportedly quipped that the Nobel Prize in Physics should go to the physicist who didn't discover a new particle that year. Murray Gell-Mann, working at Caltech, brought order to the chaos. In 1961, he proposed a classification scheme he called the Eightfold Way, a playful reference to Buddhism, that organized hadrons into geometric patterns based on their properties. It was like Mendeleev's periodic table for subatomic particles. And just as Mendeleev's table had gaps that predicted undiscovered elements, Gell-Mann's scheme had a gap that predicted an undiscovered particle, the omega minus baryon, with specific properties that the scheme demanded. When the omega minus was discovered at Brookhaven National Laboratory in 1964, with exactly the predicted properties, it was a stunning confirmation. But Gell-Mann went further. He realized that the patterns of the Eightfold Way could be explained if hadrons weren't fundamental particles at all, but were made of smaller constituents. He called them quarks, a word he borrowed from a line in James Joyce's Finnegan's Wake. 3 quarks for muster mark. In Gell-Mann's original scheme, there were 3 types, or flavors, of quarks: up, down, and strange. Protons were made of 2 up quarks and 1 down quark. Neutrons were 2 downs and 1 up. The various strange particles contained 1 or more strange quarks. George Zweig, working independently at CERN, proposed essentially the same idea at the same time, calling his constituents aces. Here's the thing, though. Quarks had a problem. Actually, they had several problems. First, nobody had ever seen one in isolation. You could smash protons together as hard as you liked, and you'd produce showers of hadrons, but never a single free quark. Second, and this was more technically troubling, the quark model seemed to violate the Pauli exclusion principle. Remember, the exclusion principle says that no 2 identical fermions can occupy the same quantum state, but certain baryons, like the omega minus with its 3 identical strange quarks, seem to require exactly that: 3 quarks of the same flavor, in the same state. Something was missing. The solution was proposed by Oskar Greenberg in 1964 and developed further by Mu-Young Han and Yoichiro Nambu. Yes, the same Nambu, who pioneered spontaneous symmetry breaking. They suggested that quarks carry an additional quantum property, a new kind of charge that comes in 3 varieties. This property was eventually given the whimsical name color. Not because it has anything to do with actual colors, but because 3 primary colors combine to make white, just as 3 quarks with different color charges combine to make a colorless hadron. Each quark can be red, green, or blue, and every observable particle must be color neutral. A proton has 1 red, 1 green, and 1 blue quark. A meson has a quark and an antiquark whose colors cancel out. And here's where gauge symmetry enters the picture again. in the most beautiful way. Just as electromagnetism arises from a local U1 gauge symmetry, the freedom to change the phase of a charged field at every point in space, the strong force arises from a local SU3 gauge symmetry, which is the freedom to rotate quark fields among their three color states at every point. When you demand that the theory be invariant under these local color rotations, you're forced to introduce 8-gauge bosons, called gluons, that carry the strong force between quarks. And because SU3 is non-abelian, just like Yang and Mills's SU2, the gluons themselves carry color charge. They interact with each other. This is profoundly different from electromagnetism, where photons are electrically neutral and don't interact with one another. Gluons are themselves colored, so they pull on each other, and this self-interaction leads to the most remarkable property of the strong force, something that nobody expected and that took years to understand, and it's called asymptotic freedom. The name sounds technical, but the idea is actually beautifully counterintuitive. In electromagnetism, the closer two charged particles get to each other, the stronger the force between them. That makes intuitive sense, right? Bring two magnets closer together, and you feel them pull harder. But the strong force does the opposite. The closer two quarks get to each other, the weaker the strong force becomes between them. At very short distances, quarks behave almost as if they're free particles, barely interacting at all. And then, as you try to pull them apart, the force gets stronger, dramatically stronger. It's like a spring that gets stiffer the more you stretch it, except even more extreme than that. This discovery was made in 1973 by David Gross and Frank Wilczek at Princeton, and independently by David Politzer at Harvard. All three were young. Wilczek was a graduate student, Politzer was also a graduate student, and what they calculated was the behavior of the coupling constant of QCD, the number that tells you how strong the interaction is, as a function of energy scale. In most quantum field theories, when you look at interactions at higher and higher energies, which corresponds to shorter and shorter distances, the effective coupling gets stronger. Virtual particles screen the charge, and as you probe closer, you see more of the bare charge underneath. That's what happens in QED. But in a non-abelian gauge theory like QCD, the gluons themselves carry color charge, and their self-interactions produce the opposite effect. Instead of screening, they anti-screen. The virtual gluon cloud around a quark actually spreads the color charge out, so as you probe at shorter distances, you see less effective charge, not more. The coupling constant gets smaller at high energies. Think about what that means. At the energies inside a proton, where quarks are packed together at distances of about a femtometer, a millionth of a nanometer, the strong force is ferocious. But if you slam two protons together at enormous energies, like they do at the Large Hadron Collider, and you probe the quarks at incredibly short distances, those quarks behave almost like free particles. You can actually use perturbation theory, the same kind of systematic calculation that works so beautifully in QED, to predict what happens in high-energy collisions involving quarks and gluons. And those predictions work. They work spectacularly well. This is why particle physicists can make precise predictions about what happens at the LHC, even though the strong force is involved. At those energies, QCD becomes calculable. But here's the flip side, and this is where it gets really deep. At low energies, at the distances relevant to everyday nuclear physics, the coupling constant becomes large. Perturbation theory breaks down completely. You can't expand in powers of a small number anymore, because the number isn't small. This is the regime of confinement, the phenomenon that quarks are never ever observed in isolation. You cannot pull a quark out of a proton. If you pump enough energy into separating two quarks, the energy in the gluon field between them becomes so enormous that it's energetically favorable for a new quark-antiquark pair to pop out of the vacuum. Instead of getting a free quark, you get new hadrons. It's like trying to isolate a single pole of a magnet by breaking it in half. You just get two smaller magnets, each with both poles. Confinement has never been rigorously proven from first principles. It's one of the great unsolved problems in mathematical physics. The Clay Mathematics Institute even lists it as one of their Millennium Prize problems, with a $1 million reward. But every numerical simulation, every experiment, every line of evidence points to it being true. And those numerical simulations, they're called lattice QCD calculations, are themselves a fascinating story. Since you can't do perturbation theory at low energies, physicists in the 1970s and 1980s, led by Kenneth Wilson, figured out how to put QCD on a discrete grid of space-time points, a lattice, and use powerful computers to calculate the behavior of quarks and gluons directly. You're essentially simulating the quantum vacuum on a computer. And as computers have gotten more powerful, lattice QCD has gotten more precise, and it now produces results that match experiment to within a few percent for things like hadron masses. You can calculate the mass of a proton from first principles, from just the quark masses and the strong coupling constant, and get the right answer. That's extraordinary. The mass of a proton is about 938 mega-electron-volts, but the quarks inside it, two up quarks and a down quark, have masses that add up to only about 9 mega-electron-volts. Where does the other 99% of the mass come from? From the energy of the gluon field, from the kinetic energy of the quarks bouncing around inside, from pure quantum field theory dynamics. When you step on a scale, almost all of your weight comes not from the intrinsic mass of your quarks, but from the energy of the strong force fields inside your protons and neutrons. That's Einstein's E equals mc squared made viscerally real. Mass, the most tangible property of matter, is mostly field energy. So by the mid-1970s, the pieces were falling into place. You had QED describing electromagnetism with its U1 gauge symmetry. You had the electroweak theory unifying the weak and electromagnetic forces with SU 2 times U1, broken by the Higgs mechanism. And you had QCD describing the strong force with SU 3 color symmetry. Put them all together and you get the standard model of particle physics, with the gauge group SU 3 times SU 2 times U1. 3 forces, 12 gauge bosons, 8 gluons, the W+, W-, Z, and the photon, 6 quarks in 3 generations, 6 leptons in 3 generations, and the Higgs boson. That's it. That's the entire inventory of fundamental fields, as far as we know, that make up everything you've ever seen, touched, or measured. Every atom, every molecule, every star, every cell in your body. The Standard Model was essentially complete in its theoretical structure by the mid-1970s, but confirming it experimentally took decades. We talked about the W and Z bosons being found in 1983. The top quark, the heaviest of the 6 quarks, wasn't discovered until 1995 at Fermilab's Tevatron Collider. It was incredibly massive, about 173 giga-electron-volts, roughly the mass of an entire gold atom packed into a single point-like particle. Nobody had expected a quark to be that heavy. The tau neutrino, the last of the leptons, wasn't directly observed until the year 2000, also at Fermilab. And then, of course, there was the Higgs boson, the final missing piece, which wasn't confirmed until July 4, 2012, at CERN's Large Hadron Collider, nearly half a century after it was predicted. That discovery was the culmination of one of the largest and most expensive scientific experiments in human history. Thousands of physicists, billions of dollars, a 27-kilometer ring of superconducting magnets buried under the Swiss-French border, all to find a single particle that exists for about a zeptosecond before decaying. And it worked. The Standard Model, this intricate tapestry of quantum field theories woven together with gauge symmetry and spontaneous symmetry breaking, has passed every experimental test thrown at it. Its predictions have been confirmed to extraordinary precision. The magnetic moment of the electron, calculated in QED, agrees with experiment to about 1 part in a trillion. The masses of the W and Z bosons, predicted from the electroweak theory, matched their measured values. Cross-sections for particle production at colliders match QCD predictions. It is, by any reasonable measure, the most successful physical theory ever constructed by human beings. And yet, it's not the end of the story, because for all its astonishing success, the Standard Model has gaps, glaring, frustrating, beautiful gaps that tell us it cannot be the final word. Gravity isn't in it. The Standard Model describes 3 of the 4 fundamental forces, but it has nothing to say about gravity. General relativity, Einstein's theory of curved spacetime, stands apart, speaking a completely different mathematical language. Every attempt to quantize gravity the way we quantized electromagnetism, to write down a quantum field theory of gravitons the way we have a quantum field theory of photons, runs into infinities that cannot be tamed by renormalization. The theory is non-renormalizable. At energies approaching the Planck scale, around 10 to the 19th giga-electron-volts, the Standard Model and general relativity collide, and we simply don't know what happens. Then there's dark matter, which makes up about 27% of the energy content of the universe, but isn't accounted for by any Standard Model particle. There's dark energy, which makes up about 68% and is even more mysterious. There's the matter-antimatter asymmetry. The universe is made almost entirely of matter, but the Standard Model predicts that the Big Bang should have produced equal amounts of matter and antimatter. Something tipped the balance, and we don't know what. Neutrinos have mass, which the original Standard Model didn't predict, and incorporating neutrino masses requires extending the theory in ways that aren't fully understood. And then there's the aesthetic problem, which physicists take more seriously than you might think. The Standard Model has about 19 free parameters, numbers like particle masses and coupling constants that have to be measured experimentally and just plugged in. The theory doesn't explain why the electron has the mass it does, or why there are 3 generations of quarks and leptons instead of 2 or 17. It works, but it doesn't explain itself. So the search continues. String theory, loop quantum gravity, supersymmetry, grand unified theories that try to merge SU3 and SU2 and U1 into a single larger gauge group. These are all attempts to go beyond the Standard Model, to find the deeper structure underneath. Some of them are extraordinarily mathematically beautiful. None of them have been experimentally confirmed. We're in a strange and humbling place in the history of physics, where our best theory is breathtakingly successful and obviously incomplete at the same time. But here's what I find most remarkable about the whole journey, and it's something worth sitting with as you drift off tonight. It's something about the nature of the whole enterprise, the sheer audacity of what human beings have managed to figure out about reality using nothing but their minds and some very clever experiments. Think about where we started. Go all the way back to the beginning of this story. In the year 1900, Max Planck is sitting in his study, reluctantly introducing a mathematical trick, chopping energy into tiny packets, because it's the only way to make the equations match what a hot oven actually does. He doesn't believe it's real. He thinks it's a computational convenience, a placeholder until someone smarter comes along and fixes it. And from that one reluctant, almost embarrassed idea, this entire cathedral of understanding unfolds. Wave-particle duality, quantum mechanics, fields vibrating at every point in space, antimatter, gauge symmetry, the whole Standard Model. The discovery that 99% of the mass in your body comes not from stuff, not from material, but from the energy of gluon fields binding quarks together inside protons and neutrons. That the solid world you experience, the bed you're lying on, the weight of your own hand, is almost entirely the energy of invisible fields. Planck could not have imagined any of that. Nobody could have. And that's the thing that gets me every time I think about this story. The journey from Planck's reluctant quantization to the Higgs boson discovery at the LHC in 2012. That's just 112 years. In the span of a single long human lifetime, we went from not knowing that energy comes in packets to building a 27-kilometer ring under the Swiss-French border, accelerating protons to 99.9999991% of the speed of light, smashing them together millions of times per second, and finding the exact particle that gives mass to the fundamental building blocks of the universe. That's not just impressive engineering or impressive physics. That's something almost unreasonable about the capacity of the human mind to reach into the deepest structure of nature and pull out truths that are stranger than anything we could have invented. And here's what's really worth marveling at. The tools that got us here, the mathematical frameworks, the physical intuitions, the experimental techniques, none of them were obvious. At every single step, the people who pushed this forward had to fight against their own common sense. Planck had to accept quantization, even though it made no intuitive sense. Einstein had to accept that light was both a wave and a particle, even though that seemed contradictory. Dirac had to accept that his equation predicted a particle nobody had ever seen, the positron, and trust the mathematics over his own discomfort. The physicists wrestling with infinities in the 1930s and 1940s had to accept that renormalization worked, even though it felt like sweeping problems under the rug. Yang and Mills had to accept that their beautiful gauge theory predicted massless particles that didn't exist, and then wait nearly 20 years for someone to figure out how symmetry breaking could fix that. And the experimentalists, Lamb with his microwave apparatus, the teams at Gargamel staring at bubble chamber photographs, Rubbia and van der Meer building a machine that could collide protons with antiprotons, the thousands of physicists at Atlas and CMS spending decades building detectors the size of apartment buildings. Every one of them had to commit years of their lives to testing ideas that might have turned out to be wrong. That willingness to be wrong, to follow the math even when it leads somewhere uncomfortable, to build machines that push the absolute limits of what's technically possible just to check whether nature agrees with your equations. That's the engine that drove this whole story. And it's still running. Right now, tonight, as you're lying here listening to this, experiments are underway all over the world that are trying to find the next piece of the puzzle. Deep underground, in mines and tunnels shielded from cosmic rays, detectors made of ultra-pure xenon or germanium or sodium iodide are sitting in the dark, waiting for a dark matter particle to bump into an atomic nucleus, The probability of any single interaction is absurdly small. These experiments might run for years and see nothing, but if they see something, even one convincing signal, it would blow the Standard Model wide open. We'd know that there's a particle out there that interacts with ordinary matter through some force we haven't identified yet, and the race would be on to figure out what it is and how it fits into the larger picture. Meanwhile, neutrino experiments are probing one of the most subtle mysteries in all of physics. We know neutrinos have mass because we've observed neutrino oscillations. A neutrino created as one flavor can spontaneously change into another flavor as it travels, which is only possible if the different flavors have slightly different masses. This was confirmed by the Super Kamiokande experiment in Japan in 1998 and the Sudbury Neutrino Observatory in Canada in 2001, and it was a genuine surprise because the original Standard Model assumed neutrinos were massless. The masses are tiny, at least 1,000,000 times smaller than the electron mass, and nobody knows why they're so small. There are theoretical ideas, like the seesaw mechanism, which postulates the existence of extremely heavy right-handed neutrinos that we've never seen, and whose extreme heaviness would explain why ordinary neutrinos are so light. It's an elegant idea, but it's unconfirmed. Experiments like DUNE, the Deep Underground Neutrino experiment being built between Fermilab in Illinois and the Sanford Underground Research Facility in South Dakota, will shoot beams of neutrinos through 1,300 kilometers of solid Earth and study how they oscillate along the way. One of the things they're looking for is CP violation in the neutrino sector, a difference in how neutrinos and antineutrinos behave, which could help explain why the universe is made of matter instead of antimatter. That's one of the biggest open questions in all of science, and the answer might be hiding in the way neutrinos change flavor as they travel through rock. And then there are the collider physicists, who haven't given up on finding new particles, even though the LHC hasn't found supersymmetric partners or extra dimensions or any of the things that some theorists predicted. The LHC is still running, still collecting data, and its high luminosity upgrade, scheduled to begin operations around 2029, will increase the collision rate by a factor of 5 to 10. More collisions means more chances to spot rare processes, subtle deviations from Standard Model predictions that might point toward new physics. There are also proposals for future colliders, a future circular collider at CERN that would be nearly 100 kilometers in circumference, or a muon collider that would use muons instead of protons to achieve higher effective collision energies in a smaller ring. These machines, if they're built, wouldn't come online until the 2040s or 2050s, but the planning and research are happening right now. The people designing these machines are betting their careers on the idea that there's more to find, that the Standard Model isn't the final word. And you know what? The history we've walked through tonight gives you every reason to think they're right. Every time physicists thought they had a complete picture, something unexpected showed up. Classical physics seemed complete until blackbody radiation broke it. Quantum mechanics seemed complete until Dirac showed it needed to be relativistic. QED seemed complete until the zoo of hadrons demanded an explanation. The quark model seemed complete until you needed color charge to explain why certain combinations existed and others didn't. At every stage, the theory that worked beautifully within its domain turned out to be a piece of something larger. There's no reason to think the Standard Model is any different. But here's the humbling part, and maybe the part that's most appropriate for this time of night, when the world is quiet and your thoughts can slow down and just sit with something big. We don't know what comes next. For the first time in several decades, there isn't a clear experimental anomaly pointing the way forward the way the lamb's shift pointed toward renormalization, or the way the proliferation of hadrons pointed toward quarks. The Standard Model is too good. It passes almost every test we throw at it. The Higgs boson mass is consistent with the simplest version of the theory. No new particles have shown up at the LHC beyond what was predicted. The theorists have ideas, lots of ideas, beautiful ideas. But nature hasn't yet told us which one, if any, is right. Some physicists find this frustrating. Others find it exhilarating. It means the next breakthrough, when it comes, will probably be a surprise. It'll come from an experiment nobody expected to be decisive, or from a theoretical insight that reframes the question in a way nobody anticipated. That's how it's always happened. Planck wasn't trying to invent quantum mechanics. Dirac wasn't trying to predict antimatter. Anderson wasn't looking for positrons when he found them in his cloud chamber. The biggest discoveries in this field have a habit of arriving sideways when someone is looking at something else entirely, and maybe that's the deepest lesson of quantum field theory, not just as physics, but as a way of understanding how knowledge works. You start with a small, strange observation. Energy comes in packets. You follow the thread honestly, even when it leads somewhere uncomfortable. You build mathematical structures to capture what you found, and those structures turn out to predict things you never imagined. You test those predictions, and when they're confirmed, you've learned something genuinely new about the universe. Not just about how it behaves, but about what it's made of at the most fundamental level. Fields, excitations of fields, interactions governed by symmetries. That's what everything is. That's what you are. You're a temporary, beautifully complex pattern of excitations in quantum fields. The electrons in your body are excitations of the electron field. The quarks inside your protons and neutrons are excitations of the quark fields. The forces holding you together, the electromagnetic force keeping your atoms intact, the strong force binding your nuclei, are mediated by photons and gluons, which are excitations of their respective gauge fields. And the mass that gives you weight, that pulls you down into your bed right now, comes mostly from the energy of those gluon fields, churning and self-interacting inside every proton and neutron in your body, plus whatever the Higgs field contributes to the rest masses of your quarks and electrons. You are, in the most literal and precise sense that modern physics can offer, a localized excitation of the quantum fields that permeate all of space-time. That's a strange thing to be. It's also, I think, a wonderful thing to be. Because those fields are everywhere. They extend across the entire universe. The electron field here in your room is the same electron field that exists in the Andromeda galaxy, 2.5 million light-years away. When an electron is created in a distant star, it's an excitation of the same field that your electrons belong to. In a very real sense, quantum field theory tells us that everything is connected, not in some vague mystical way, but in a precise, mathematical, physical way. The fields are the common substrate. We're all ripples in the same pond. So as you lie here, and your breathing slows, and the details start to blur, the gauge groups, and the Lagrangians, and the Feynman diagrams, and the symmetry breaking, let them go. You don't need to hold on to all of it. What matters is the shape of the story, the arc of it. That human beings, starting from almost nothing, armed with curiosity and mathematics and a stubborn insistence on checking their ideas against reality, managed to uncover this hidden architecture of the universe, that the world is made of fields, that symmetry dictates interaction, that the vacuum isn't empty, that mass is mostly energy, that the laws of physics are the same everywhere, for everyone, and that we can know them. That's enough. That's more than enough. The rest, the parts we haven't figured out yet, the dark matter and the dark energy and the quantum gravity and the 19 unexplained numbers, those are problems for tomorrow. For tonight, just rest in the knowledge that the universe is comprehensible, that it has structure, that the structure is beautiful, and that you're part of it. Every atom in your body was forged in a star, and every particle in every atom is a vibration in a field that stretches across all of space and time. You're woven into the fabric of reality itself, and that fabric, as far as we can tell, is made of mathematics and light and symmetry, humming quietly beneath everything, holding it all together, even now, even here, even as you drift off to sleep.